Dear students, last class we discussed about Lagrange's interpolation. Now we are almost at the end of the fifth module. I told you about the interpolations in the last class. What is interpolation and extrapolation? We know the interpolation and extrapolation and also Lagrange's interpolation. Now we are going to discuss about two more interpolation, that is forward and backward interpolation along with divided difference interpolation. To know about forward and backward interpolation and divided difference interpolation, we need to know the concept of finite differences. In finite differences, we have three types of finite differences. One is a forward differences, the second one is a backward differences, the third one is divided difference. So in this class, I will give the introduction for forward and backward interpolation, that is forward difference and backward difference. Afterwards, we'll discuss about the divided difference interpolation. Okay. Now, I told you these all three interpolation comes under finite differences. When you have a function y is equal to f of x, some unknown function. For some function, we will give the values of x. We call the values of x as argument, and the values of y, we called it as entries. The corresponding values of y for x. When x is equal to x0, you will get y as y0. When x is x1, y is y1. Similarly, y2, y3, etc., yn. Now, I will define what is forward differences. Delta represents the first order forward difference. So this is the notation for a forward differences. And it is defined by delta yn minus 1 is equal to yn minus yn minus 1. Here I am defining for a nth term. Using this, we can define for the first entry, second entry, third entry, etc. Here, this is the definition for nth term. And observe the power of the delta here is 1. So this represents first order forward difference. So this is the definition of first order forward difference, where n belongs to any positive integer. Means n can take the value from 1 to infinity, positive value. For example, when you replace n is equal to 1 here, you observe here, when you replace n is equal to 1, this expression reduces to delta y0 is equal to y1 minus y0. So this is the definition of the first order forward difference of the first entry. Similar to that, when I take n is equal to 2, this expression reduces to delta y1 is equal to y2 minus y1. So this represents the first order forward difference of y1. Similarly, we can define for the second and the third entry y2 and y3, etc. Here, delta y0, delta y1, delta y2, etc. are called first order forward differences. Observe the power is 1 here. So we call it as first order forward differences. We know the another operator differentiation, d by dx. When you differentiate the function f of x with respect to x once, we call it as first order derivative. When I differentiate the same derivative with respect to x again, we call it as second order. If I differentiate this again, you will get third order, similarly higher order differentiation. On the same manner, here also we can define the higher order forward differences. Now I will explain how to find the second order forward difference. The differences of the first order forward differences are called second order forward difference. That is, observe the first order forward difference of y0. The first order forward difference of y0 is y1 minus y0. Observe the second order forward difference of y0. This gives delta y1 minus delta y2. These two are the first order forward difference. The difference of the first order gives the second order. Similar to this, observe here, the difference of the first order forward differences gives the second order. Okay, and I gave one more example. Similar to the second order, we can define the third order difference also. The differences of the second order forward differences are called the third order forward differences, and it is denoted by delta cube of any entries, delta cube y0, delta cube y1, delta cube y2, etc. And we can find out higher order forward differences, and usually we are going to construct a table. Means we are arranging these forward differences in a tabular column. We called this tabular column as forward difference table. For your convenience, I will give one example here. Observe this table. First column having the values of x, this is a given data, x0 to x6. Second column is a function, the value of y, and this is also given, y0 to y6. Your calculation starts from the third column. So this is my first order forward differences. And first I am going to define the first order forward difference for the first entry, y0. So observe the definition here. What is y0? Delta y0 is y1 minus y0. So according to that, so y1 minus y0, observe the arrow mark, y1 minus y0 gives delta y0. So what is delta y1? y2 minus y1 gives delta y1. Similar to that, delta y2 is nothing but y3 minus y2. This gives delta y2. Similarly, we can find out delta y3, y4 and y5, but I can't find out delta y6 here. I'm not mentioning anything here because according to the definition, delta y6 is y7 minus y6, but I don't have a y7 value. So this is not possible. In the beginning, I have 7 values of y, but when it comes to the first order, I will get only 6 values. So one value will decrease. After finding the first order forward differences, I need to go for a second order forward difference. Observe the table. No need of definition to construct the table. So to find out the second order forward difference of delta y0, delta y1 minus delta y0 gives the second order forward difference of y0. Delta y2 minus delta y1 gives the second order forward difference of y1. Similarly, delta y3 minus delta y2 gives the second order forward difference of y2. On the same manner, we can find out these two. After this, we can go for third order. Same process. Delta square y1 minus delta square y0 gives delta cube y0. Delta square y2 minus delta square y1 gives delta cube y1. On same manners, we can find out the fourth order, fifth order, sixth order, etc. In this example, we can find out up to only sixth order. I can't find the seventh order because to apply addition or subtraction, we need a minimum 2 numbers. In a sixth order, I have only one element here, so I can't go further. Sometimes here all the elements may be 0. In that case, no need to find the sixth order also, because 0 minus 0 gives 0. We know that. So in that case, we can stop here. Sometimes here only all the elements may be 0. In that case, we can stop here. We need to complete the table in such a way that in the last column, we need at least one element, or all the elements of that column is 0. So that completes the forward difference table. Now in this table, the first element from the third column are called leading forward entries. Okay. So this is from the third column. So delta y0, delta square y0, delta cube y0, delta power 4 y0, delta power 5 y naught and delta power 6 y naught. So these terms are called leading forward entries. I am going to use these leading forward entries in a forward interpolation formula. So this is the basic concept for forward interpolation and extrapolation formula. Now I will give what is forward interpolation and extrapolation formula. To find a y at a given point of x, x may be anything between the range or outside the range. If x is between the range, we call it as interpolation. If it is outside the range, we call it as extrapolation. The forward interpolation formula is given by, observe the formula very carefully. We are finding y at a given point of x. The first term is y naught, means the initial value of y, plus r into delta y naught. I will tell you how to find r or what is r later, plus r into r minus 1 by 2 factorial into second order forward difference of y naught, r into r minus 1 into r minus 2 by 3 factorial into third order forward difference of y naught, plus etc. Where to find out r, the formula is x, that is at some point of x we are finding y, so consider that x here. X naught is nothing but the initial value of x divided by step length. We know step length already. The difference between the consecutive values of x is called as step length. For example, if x is 0, 1, 2, 3, 4, 5, 6 like that, the difference is 1. So that is step length. Sometimes the values of x may be 0, 2, 4, 6, 8. In that case, the difference is 2. So the step length is 2. Okay. Now, first term is y naught, that is the initial value of y. What about this? Delta y naught, delta square y naught, delta cube y naught, delta power 4 y naught are called leading forward differences. Observe the previous slide, the table. Delta y naught, delta square y naught, delta cube y naught, delta power 4 y naught, etc. So these are called leading forward differences. So these terms we are going to use in a formula. So when you are going to construct the table, you have to be very careful. So this is forward interpolation and extrapolation formula. Now similar to this, I'm going to define backward difference. This is the notation for a backward difference operator. We call this one as del, D-E-L, del, the reverse notation of delta. And it is defined by del yn is equal to yn minus yn minus 1. Here also n is a positive integer. Okay, means I can take n is equal to 1, 2, 3, etc. I can't take 0 because when I take n is equal to 0, here yn minus 1 reduces to y minus 1. This is not defined. So n starts from 1, 2, 3. Now using this, I'm going to define the first order backward differences. When I take n is equal to 1, this nth term reduces to del y1 is equal to y1 minus y0. Similarly, when I take n is equal to 2, this reduces to del y2 is equal to y2 minus y1 and etc. So here this del y1, del y2, del y3 are called first order backward differences. Similar to forward differences, here also we can define the higher order backward differences. That is, the differences of the first order backward differences are called second order backward differences. The same concept. Del square y2 gives del y2 minus del y1. Del square y cube, del square y3 gives del y3 minus del y2 and etc. And then we can define the third order backward differences. That is, the difference of the second order backward differences gives the third order backward differences. And the relation is del cube. Similar to forward difference table, here also we can construct the table. We called it as backward difference table. Same example I am taking here. The first column represents the values of x. I am taking this almost similar example, that is x0 to x6 and y0 to y6. I told you already, I can't define del y0 because to define this I need y0 minus y minus 1. So this is not defined, so del y0 is not possible. So the first definition is del y1. So to define this, y1 minus y0 gives del y1. y2 minus y1 gives del y2. y3 minus y2 gives del y3. Similarly, the remaining. Now to define the second order backward differences, del y2 minus del y1 gives del square y2. Del y3 minus del y2 gives del square y3. Similarly, the difference of these two gives del square y4. The difference of these two gives del square y5 and del square y6. Almost similar manners, we can find out the third order differences. Okay, that is the difference of the second order for backward differences gives the third order. Similarly, I can go for fourth order, fifth order, sixth order. Same thing here. In a sixth order, I have only one element, so I can't go for seventh order. Okay, so this is my maximum. In a forward difference table, the first element from the third column are called leading forward entries. Similar to that, here also the last element from the third column. So the last element from the third column are called leading backward entries. Is that clear? In a forward difference table, the first element from the third column are called leading forward entries. But in a backward difference table, the last element from the third column are called leading backward entries. Now I will give what is backward interpolation and extrapolation formula. Same thing, here also we are finding the value of y at some point of x. The formula is, you have to be very careful in a forward and backward interpolation formula because observe the formula looks similar to the forward. Now, y of x is equal to yn plus r into del yn plus r into r plus 1. But in forward, here we have a minus. That is the difference. In a forward interpolation, we have r minus 1, r minus 2, r minus 3, etc. But in backward, we have r plus 1, r plus 2, r plus 3, etc. And in a forward interpolation, we are using leading forward entries, but in backward interpolation, we are using leading backward entries. That is the last element from the third column. These are the last element from the third column. I'm going to use these values in a backward interpolation formula. And there is a difference in to find out r also. Here to find the r is x minus xn by h. But in forward, the formula is x minus x naught by h. Because forward, we are going to take initial value. This is a backward, we are going to take the final value of x. So you have to be very careful when you are going to consider the forward interpolation formula and backward interpolation formula. But here, both the formula working procedure remains the same. There is no difference. And both the procedure, at the end, we are going to find the value of y. So, in which case we can apply the forward and backward interpolation formula. For that, observe these two notes. You are finding the value of y at some point of x. Okay, I am finding y at some point of x. If this x is nearer to x0, prefer forward interpolation formula. Otherwise, if the given x is nearer to xn, prefer backward interpolation formula. So you need to be careful about these two statements. When the given x is nearer to x0, I am going to use forward interpolation formula. And when the given x is nearer to xn, I am going to use backward interpolation formula. And the one more important thing is here, the table. In some problem, we may need to use both the formula, forward and backward interpolation formula. In that case, no need to construct forward table and backward table, because the table values are almost same. There is no difference. Just the notation and the definition will difference, but in the example you will get to know how both are same. Okay, so now when you are going to solve the problem, just construct the forward difference table. When you are using forward interpolation formula, use the first element from the third column in the formula. But in the same table, when you are using backward interpolation formula, use the last element from the third column for a backward interpolation formula. So you have to be very careful about these problems. In the next class, in the next video, I'm going to explain the problems, means these two formula, how to use the forward and backward interpolation formula in one table, and how to find the value of y by using these two formula with an examples. Okay, thank you. And remember one more thing, you have to be very careful about this definition, because this is very important to solve the problem. So tomorrow I'm going to send one more video regarding the problems on forward and backward interpolation formula. Thank you.